Hello and welcome to KAUST Live. The International Conference for High Performance Computing, Networking, Storage, and Analysis, or SC18, kicks off in just a few short days. Now, this is the 11th year that KAUST has participated in SC18, and the director of the university's Extreme Computing Research Center, Professor David Keyes, is chairing the technical program. So he's joined us to talk about that, his research, and a whole lot more. Professor, thank you so much for joining us.
It's a great pleasure. Thank you.
So you're chairing the technical program. Give us a sense for what that means and what participants should expect.
Okay. At Supercomputing, we expect about 13,000 people this year, approximately 5,000 of whom are part of the technical program. The remainder make up a very large exhibit floor of vendors and users of supercomputing. The technical program is empowered by about 400 volunteers from our peers who are called to solicit and then select the program. In some cases, we have invited speakers, so they are, a special class, but we have technical papers from, the international audience. We have awards that we give every year on behalf of the Association for Computing Machinery and the IEEE Computer Society. We have panels, posters. We have Birds of a Feather session where people with special interests can advance their cause, meeting their international peers. We have a session on emerging technologies, a showcase for doctoral students emerging, a showcase for scientific visualization, an early career program, and I'm sure I'm missing something that my peers in Dallas next week will fault me for. But there are about 10 program elements, and we have a couple of hundred students who volunteer to do the logistics. So it's a wonderful networking opportunity above all for the thousands of people in the world who care about pushing computing to the next level, beyond the commodity level. Typically government agencies like in the US, the Department of Energy, or in Japan, RIKEN, or in China, the Academy of Sciences, which operate the world's most powerful computers for a variety of science advancing, engineering, designing, and policy making purposes.
It's the one time a year these supercomputing guys get out and sort of hang out in a group.
It's the biggest one in the US, and it is the largest one by participation. Every June there is a comparable meeting with both technical program and vendors, hot to trot their new offerings in hardware and software in Germany, typically in Frankfurt, the International Supercomputing Conference. And in recent years, both Japan and China have started domestic HPC conferences, HPC High Performance Computing. And in Saudi Arabia, we've been doing that for about, I think, 9 years. KAUST created the first one in Jeddah, so it's now called HPC Saudi. The hosting for that has rotated, I think, 3 times to KAUST, a couple of times to KAUST, and various other sponsors within Kingdom. Sometimes Intel just does it out of a hotel. But the last one was very successful at King Abdulaziz University last spring. So we're very happy to be incubating an HPC culture in Saudi Arabia too.
Right. What is the rationale? I mean, since KAUST has been in the SC game for more than a decade, so.
Right.
But what goes into it, and why does KAUST participate?
Yeah, well, actually, that's a bit of a sentimental question for me, because the first time I ever heard the acronym KAUST was at the 2007 Supercomputing Conference, when a colleague of mine who had just returned from the Information Technology Summit that was conducted in Riyadh as part of KAUST's formative consulting with international leaders, he told me that Saudi Arabia was about to create a university that was built around computational science and engineering, and they were going to get a world-class, a top 20 supercomputer. And after I heard about that, I guess he put me in contact with the founding people from Aramco, and I got involved as the chair of the Cyber Infrastructure Advisory Committee back in 2008. And we interviewed, among other vendors, IBM, and eventually went with their system. So really, supercomputing was the beginning of KAUST for me. We then had a exhibit booth in 2008, November, in order to begin recruiting faculty and researchers who would take advantage of our supercomputing capability. And of course, when we launched KAUST in June of 2009, we had Shaheen 1, an IBM Blue Gene P, the world's 14th ranked computer at that time. and one that would still be serving simulations to us, except that, over time, the state of the art in hardware advances so quickly that that machine would be a couple of orders of magnitude too energy inefficient right now to keep it going. But we've had a booth at Supercomputing ever since that time, primarily for recruiting purposes, to just tell the world who we are and that Saudi Arabia is a supercomputing country. In fact, in 2009, there were only 2 countries in the world that had a faster supercomputer than Shaheen 1. They were the United States and Germany. Since that time, Asia, as we know, has embraced supercomputing with wild abandon. For many years was leading the list of top computers. Just last June, the U.S. retook that lead. We don't know for how long, with Summit, the new IBM NVIDIA computer at Oak Ridge National Labs. And this race, if you will, like the space race in the 60s, to become I guess the most powerful simulator to lead policy decisions continues, and Saudi Arabia is right in the middle of it. To outcompute is to outcompete, as the saying goes. I see.
Well, and so that raises an interesting question, particularly for people outside of the supercomputing realm. I guess in the popular imagination, people see supercomputers beating world chess champions or doing Watson type stuff. But give us a broader sense for what supercomputers are doing.
Well, a supercomputer is, in my opinion, above all, a universal scientific instrument. Astronomers have their telescopes, chemists have their spectrometers, oceanographers have their deep sampling vessels, and so forth, but all of them take advantage of the vast memories and the ability to marshal and process data on supercomputers. Traditionally, supercomputers were born in the 1940s to assist the U.S. with its nuclear weapons development, neutron transport, and they were also used very early in fluid mechanical simulations, including, believe it or not, in the 40s, the weather. In fact, you can go back to 1922 and find a paper that was written before any digital supercomputers had ever been conceived or built about how to predict the weather by discretizing the underlying continuum equations, mass, momentum, energy, conservation, and sort of building a model of the world with a certain number of observers, every distance, in kilometers or whatever, and passing data back and forth about how the pressure was changing. And eventually this empowered the vision of stored program digital computers, and we've been on that track since the mid-1940s. And today, a computer, can hold many hundreds of petabytes of data in its live DRAM memory, which allows very highly resolved simulations of terrestrial and other phenomena. For example, the Gawar Reservoir here in Saudi Arabia has about 1 trillion cubic meters of, oil-bearing rock. We can fit a 1 trillion cell model of Gawar, in fact we have on Shaheen, into today's computer memories, and then we can drive it artificially with different wellheads to inject and to recover, and run different scenarios to maximize, in advance of actually turning on the tap, the best way to produce that reservoir in terms of not leaving oil behind, because when you drive in water or a gas to drive the oil out, it typically fingers, and you might leave behind large pockets of oil, and this makes it harder for them to be found and recovered later. So that's just one example of simulation. Of course, everybody wants to predict the weather. Will my picnic be rained on? The weather is a chaotic dynamical system. You can't integrate it indefinitely into the future in a deterministic way. But as you know, during our lifetime, weather prediction has gone from about a day to a good couple of weeks with pretty good reliability. That's due to improved models, finer and finer grids around the Earth, more and more physics put into every grid point. And the existence of a resource like that then produces people who want to improve the scientific models. What is the cloud albedo? What is the terrestrial release of oxygen from trees? These phenomena are worthy to study, more and more carefully as the models that can, represent You know, their outworking become finer and finer grained. But basically, I think of a computer as a huge amount of memory, and you know, you can put in there and retrieve and manipulate whatever you want.
So what you're saying is that Weatherman took the fall, but it was really supercomputing that needed to catch up and get them up to speed. Interesting.
Yeah. Of course, climate prediction, we take that hundreds of years into the future, but we do that in a statistical way. We don't pretend to say what the temperature will be in Jeddah in 2050, but we know, you know, within a high probability what bands of temperature will persist on different days and so forth.
Well, and so that brings up an interesting point, I think. You know, KAUST doesn't build supercomputers, but KAUST does something very integral to the use of supercomputing. Talk a little bit about that work and the ECRC in general, which you're a director.
Yeah. Well, first of all, I'd like to mention that about 46% of the current KAUST faculty have accounts for themselves or their scientists on our current supercomputer Shaheen 2, a Cray XC40, which entered the world at number 7 and is now about number 29 after a passage of years during which others, particularly in Asia, are rapidly adding to our global simulation capability. But that's 68 out of our 150 faculty who are actively engaged as part of their scientific discovery, part of their engineering design in simulations or in big data analytics. So that is a computational science university for you. Most of them are using codes that are in the public domain or that are licensed from commercial software vendors. For instance, in chemistry, there's a number of codes that you actually pay dearly for to license. In climate modeling, all the codes are open source. You know, they're shared internationally. There are different cultures in different fields. But in any event, we are mostly a community of users, but the ECRC among that group is about a dozen faculty who consider themselves primarily developers. So we look at our job as getting a good return on investment in the sense of making our computations more efficient, in looking at the inner kernels, the linear system solves, the grid traversals, the fast Fourier transforms, the things that other users expect to have there as, you know, a low-level mathematical operation. We try to graft that on to emerging hardware as efficiently as we can. If you look at the history of supercomputing or computing in general, it used to be that the arithmetic operations were the most expensive and time-consuming part. But after decades of Moore's law, the transistors that make up those arithmetic devices are now extremely fast and very low power. And the dominant cost in supercomputing is actually moving the data around on the networks through the copper vias, which as they shrink become highly resistive and are now the bottleneck. So our job in the ECRC is to go through decades of popular algorithms and try to rework them to minimize the memory traffic. You know, once you pull up a piece of data from deep DRAM through SRAM, cache to registers, you want to keep it there and manipulate it as much as you can before it has to be replaced with the next thing you're operating on. So we're reorganizing, we're re-choreographing, the world's scientific computations to get more arithmetic intensity, to re-engineer the codes, to optimize, to minimize what's expensive, which is the communication. Think of our, XC40. I don't know if you've ever been in the machine room, but it's like a basketball-sized court, and there's, I don't know how many hundreds of kilometers of cables, both copper and, optical fiber, connecting all those cores. We have 200,000 cores on Shaheen. And really, it's not the math, it's the choreography that really determines whether you're going to be using that efficiently or not.
Right, and the storage plays a big part in that, doesn't it?
Yeah, memory hierarchies have now become very deep. I mentioned registers, cache, and several levels of semiconductor memory. Then we have the flash memory of the burst buffer, which was a Cray commercial product that we were one of the first to purchase. And then you go out to disk, and from disk you can go to the robotic tape farm and to figure out the best place for each element of your data to live at any one time. As you go deeper, you get cheaper and slower. As you go higher, you get faster and more expensive. And that's been, one of the main advances in computer architecture over the years, is to, figure out how to access huge amounts of memory at the cost, of small amounts of memory by figuring out where the data lives and how it gets replicated.
So speaking of that and the advancement of technology, the center's one of the pages talking about the mission of the center gets into, since 1988, simulation has improved by more than a factor of 1 million in performance.
Yeah.
Help lay people understand this level of development.
Yeah, so we track that number in two ways, that progress. A rather controversial way of tracking it is the so-called high-performance linear algebra benchmark. That is, in fact, the number by which the world's machines are ranked twice a year. They are allowed to solve as large a linear algebra problem as they wish in order to fill up their machine and get a lot of flops out, because the work to do that computation grows like the cube of the problem size, and the storage grows like the square. So if you make that problem size larger and larger, you do more work in a given amount of time, and you get a higher ranking for your computer. That benchmark is actually relevant to a lot of scientific computations, but certainly not universally. And many of the computations that we do here at KAUST, our combustion modeling, our climate modeling, actually don't use that operation at a large scale. So another metric to track the progress in supercomputing is the so-called Gordon Bell Prize. Gordon Bell was the head of the U.S. National Science Foundation cyber infrastructure organization for a period of time in the mid-'80s, early '90s, when supercomputing was making inroads into U.S. academia. It had been primarily a government lab thing, in the early years. And he became wealthy through his commercial work with Digital Equipment Corporation, actually, and endowed this prize, which has attracted the attention of the global community. And it's not restricted in terms of what the application is. One year it might be material science, one year it might be reservoir modeling, one year it might be climate prediction, one year it might be this year there's an epidemiological Gordon Bell nomination that we will be deciding on next week as one of the prizes. By the way, this year there are 3 AI Gordon Bell nominations. There are 6 in total, and half of them are in the field of artificial intelligence this year. That has never happened before. It's always been simulation driven, but this year is big data analytics making big headroads into supercomputing. Something that we'll be looking at carefully at KAUST, of course, in restructuring our curriculum and the remaining faculty hires that we have to do. These data scientists should be in every program, every center, to take advantage of things like machine learning.
Right.
But where was I in terms of unfolding this big onion?
Well, no, and that raises the question.
Oh, the factor of a million.
Factor of a million,
so
thank you.
it's the Gordon Bell Prize that has been actually measuring this. So there's actually 2 prizes, one on performance and one on price per installed performance. And the raw performance, as a product of Moore's law, faster transistors, more on a chip, and parallelism, more chips connected by bigger networks. Those 2 factors together have led to that performance improvement. Meanwhile, the energy per computation has been going down dramatically, as it needs to, because if you can imagine taking a power-sucking computer from 1988 and making it 1 million times larger, well, we don't have that much electricity, right? So we've been improving the computer engineering to make components smaller and more energy efficient, while we have been aggregating more of them. I don't say we, but, the international community of computer engineers. I'm one level higher than that. I'm an algorithms designer, and then there are people at KAUST who are a level higher still, the actual applications designers and users. But this factor of a million is unprecedented. If you sped up air traffic by a factor of a million, you could get from here to Tokyo, say, in 1/20th of a second, instead of the dozen hours that it takes.
We'd be a teleportation.
Yeah, you'd still spend 3 hours in the airport, and that's the problem of I/O, the slow disks and setting up the computation. But there's no field of human endeavor other than the ones that are in fact powered by supercomputing that have ridden such a dizzying curve of technology. In jet engines, we're happy if from one decade to the next we get maybe 2% more efficiency, a little bit less greenhouse gases, flying more passengers for, the same liter of jet fuel. But things that ride the supercomputing surf, like, for instance, the human genome, which is mostly a computational problem. I mean, you sequence, you go into the lab, you take your spit or your other, sample, you sequence it, and then you spend days to weeks to months on the computer trying to match that sequence, put it back together from the tiny pieces and match it against other whatever you're looking for in terms of the areas that indicate some kind of a disease or some kind of ethnic inheritance or whatever.
Right.
And it's that part of the genome that has been dropping in price and in time with the advent of supercomputing, so that you can now sequence yourself for $100.
Right.
And
why do you think that is? I mean, why such rapid progress in this area?
It's a product of many factors. Hardware is at the base of it. In 1965, Gordon Moore of Intel extrapolated 3 points from 63, 64, and 65, and he said, gee, computers, we get more transistors on a chip by a factor of 2 every 18 months. And, if you just keep going on that exponential curve, you end up where we are today in terms of, the density, literally tens of billions of transistors on a, 2 centimeter square die that makes up today's Intel, let's say, Skylake chips or whatever. That's one feature. The other feature is gluing more of those together. And, if we didn't have the incentive to do it, having more memory available to simulate finer and finer grids over more and more complex phenomena, then I suppose people wouldn't have invested. A new fab line for a new semiconductor chip costs several $1 billion. It's like designing a new airplane, designing a new chip. Between the time that you conceive of the devices and the time that you're doing the lithography and the packaging and getting it out the door. And so it's an amazing capital investment up front, and the faith has to exist that you'll be selling billions of them, and that people will figure out more and more interesting things to do with them. I guarantee that when the physicists who designed the World Wide Web to share data from the Large Hadron Collider, well, what was in those days, CERN, it wasn't the Large Hadron Collider then, I guarantee they weren't thinking that their kids would be ordering sneakers over the internet just a couple of decades later. But as we know, the commercial market for information technology is approximately 100 times larger than the scientific market. And that's actually one of the challenges we face as scientists, that the chip makers are motivated to design for a different point in supercomputing space than we find easiest to harvest. So we're using graphical processors to do scientific processing. They weren't set up. They're not ideally proportioned for what we want to do, but because they're commoditized, they're so cheap, and that's an incentive for our from our side to take advantage of them.
So for example, gaming driving visualization advances.
That particular technology, or the low power technology that lets your cell phone battery last longer. That's another commercial driving force that has been in effect influencing supercomputing.
Yeah. What other areas then is supercomputing going to look to reach into in the near future?
Well, anything that wants to aggregate a lot of data and compare it. So, of course, there are both noble things there and sinister things ahead for large-scale computing. But certainly the growth area these days is in artificial intelligence, in particular one classification branch of artificial intelligence that we speak of as deep learning, which is a multi-layer neural net. It turns out that the operation that teaches the neural net, first you train the net and then you infer from it. The training step is the long step. That's, you might take 3,000 hours of video and pedal motion and steering wheel thing to train a car, to drive. And then it can drive in real time after it's trained. But that training turns out to maximize that HPL benchmark operation that I spoke of earlier.
Okay.
And so that is actually one of the really high growth areas in supercomputing today. Up until a couple of years ago, you wouldn't have found that topic at our supercomputing meeting. It was being done at much smaller scale by academic pioneers. But now every company, every society, with government labs that's collecting data and wants to be one step ahead of the competition, every financial firm, doing actuarial demographics or doing real-time, stock tracking, they need to think faster than humans. They need to train machines to see patterns and to act upon those patterns faster than humans can understand them. And so supercomputing is, I think, going to be driving national investment for a long time. It's not only making scientific discoveries and inferences, it's also cryptography is very much empowered by bigger computing. All the crypto schemes require that you can stay ahead of the competition in terms of being able to factor prime numbers, for example. So that's in fact, that leads on to another issue, which is quantum computing, a totally different technology from today's deterministic digital computing, which may have very little replacement of our PDE models, our partial differential equation models by which we do simulation, but it may make huge inroads into other discrete problems, including cryptography, where you want to sample billions of things very quickly and then come up with probabilistically the best one.
Well, what sort of nuggets of wisdom do you have for young scientists coming into this field, or just into international science in general?
Well, everybody should probably think of taking, some computer science courses that, first of all, enable them to not be intimidated, right? I mean, once you've written your own program, programming is no longer so mysterious. Once you have, invoked some model and tweaked the knobs and see, if I put more rain in there, the salinity changes there. Once you actually, I mean, these are things that are intuitive, but when you see that you can actually manipulate such systems in a simulated way in real time, suddenly you're not intimidated by all of the statistics that come your way in terms of different controversy in climate prediction, different statistical results in, for instance, medical treatments and so forth. You get inside and you see, there's a lot of uncertainty here, there's a lot of judgment being made here. I can be a critic, and I think that's the most important thing for a young scientist, is to be a critical thinker about this third modality of scientific investigation. If we go back to theory and then experiment and then the modern scientific method being born when theory and experiment were corroborated, and now we have a third modality of simulation and a fourth modality of statistics discovered patterns without even having a model. For example, in human behavior, we don't have conservation laws of mass, momentum, and energy, but we can predict what humans will do on average when they buy this product. They may buy that product. These are statistical models. They're not physical models. And so we now have these four ways of knowing, and a young scientist should make friends with all of them. Doesn't have to be an expert in every one of them, probably can't be, but should be a critical thinker about all of them.
It strikes me as you're talking that a lot of supercomputing technologies and computing technologies come out of the garage. They come out of people experimenting like this. I mean, again, that seems like something that you're encouraging students to do. Talk about the legacy of supercomputing from the garage and how students can maybe get involved in some of that. And we have a very sort of entrepreneurial culture here with a makerspace and some other things, but how do students get their hands on that first simulation? Or
Well, you referred to entrepreneurialism. In fact, I was the founding dean in the math and computer science and engineering division here at KAUST, and I think our first 5 student-generated startups, 4 of them were in the IT space. Right. I used to use that slide in my what is KAUST talk, because after all, the investment to create a software universe is quite small compared to prototyping some physical device. And it is sort of a digital workbench. You can take advantage of a lot of tools that offer a high-level programmer interface, like MATLAB, for example, which has many engineering toolboxes on top of it. And you, with a high-level, applications programmer interface, you can create, a system of circuits, or a system of, pipes, or a system of, other engineered components, and play with it, and get an idea of how such a thing would behave in practice. In fact, I certainly, I always am very humble in the simulation world to say, ultimately it's experiments that determine, because computer models have a lot of known errors and uncertainties. What are the initial conditions? What are the boundary conditions? Does the model really satisfy these equations, or is it really something more complex? What simulation and experiment can do together is simulation can lead lead experiments into those places in parameter space where the expensive experiments are finally performed to verify the simulation. So it's a virtuous cycle, and the ability to go back and forth from those two sides, starting from high school or undergrad or early courses, and just beginning to think of these complementary modalities. What are humans good at? What are machines good at? What is the laboratory good at? And be fluent and build up a network so that you can draw upon expertise in the other areas. That's, I think, the key to being, for a young scientist today who wants to, track the frontier.
Right.
The frontier is going to be multidisciplinary.
The one area that I think many of us hope doesn't get taken over by supercomputing, of course, is music. And you're known on campus not only as a director but as a musician. So talk about how performing music plays a role in your life.
Well, sure. By the way, artificial intelligence has made great inroads into composing music. You can, just as you can, take a photograph and say, render this as Van Gogh would, or as Renoir would. You can actually give a simple, few note motif to computer programs today and say, compose that like Mozart would, compose that like Strauss would, and so forth. And these are remarkably successful. I mean, really an expert could be fooled. Oh, I didn't know Mozart wrote that sonata. So that is, that is coming. So don't be too confident that humans won't create art that we love and are actually fooled by. Of course, it's imitating a human mind's product, but it's imitating it very well. Right. But on the performance side, music and math go back together to Pythagoras. He was the first recognizable mathematician, and he was the first recognizable music theorist. He created the scale, the 12 note scale that we use in Western music, was something that he realized could be built from whole number ratios of subdividing a vibrating string. So, and several of the world's most famous mathematicians have written in music theory. Euler, for example, the guy who gave us natural logarithms and exponentials and modern analysis, the notation f of x for functions, all this was out of Euler's mind. He wrote 2 books on music theory. So, there's a pattern seeking part of the human brain that finds music intriguing. I think it was Leibniz who said that music is the soul counting. There's patterns of rhythm, there's patterns of pitch, there's patterns of repetition, of frequency, intervals, and the human brain, without question, is wired for certain resonances, in terms of pitches that it likes, sequences that it likes. I mean, this is fairly cross-cultural. I mean, musicologists and ethnologists and so forth have studied this. I haven't, but I've read a little bit, and I think it's very often you find that people who are attracted to mathematics are also attracted to music. I would say there are many other people who are attracted to music who don't have the privilege of seeing maybe at a young age its mathematical connection and don't make that connection. Of course, they can still enjoy music in a very deep way, but the two often are associated. I've never consciously thought of one or the other. I enjoyed both as a young person, and in fact, if it weren't for my mother forcing me away from my piano teacher at about age 17, I might well have been a struggling musician today. But fortunately, I joined a more supportive vocation. And you know, if you're amused by my frequent appearances on KAUST stages, I should tell you that for about 35 years, my music was totally dormant. I mean, when I started my career as an assistant professor, I just, you know, gave up music. I mean, I loved it, but I didn't have time. You know, it's very clear what you have to do. And it was actually coming to Saudi Arabia that my musical interests were reawakened. And if that seems ironic, think of the following. Within my zip code, living on Broadway in Manhattan, there were probably 1,000 pianists, maybe 10,000 pianists better than me. But when I got here, there were all these students who wanted an accompanist, and you know, well, the complete dean should be the accompanist for his students, right? So, so I really have had a wonderful time with KAUST musicians, most of them amateur, like myself. I don't think of it as bringing math to the stage, but I do have a winter enrichment program lecture on that topic if you ever want to get into it.
Indeed. Well, we certainly hope you're not replaced by a supercomputer in this regard anytime soon, and we really appreciate your coming by to speak with us before heading off to Dallas.
Thank you, Nicholas. Yeah. I'm very grateful for this opportunity and for your interest and the presumed community's interest in keeping KAUST on the map in supercomputing, and not just processing it, but you know, leading and advancing supercomputing to the next level. It's a great privilege.
Right. Thank you. And that's all the time that we have for today. Remember to comment, like, and share on all the KAUST social channels. And from everyone here at KAUST, thanks for watching.